Hey, it's me again. All right, so I'm going to talk about volume for your asynchronous week 2. Officially, this video is week 2, even though I'm recording it in week 1, and you might be watching it in week 1. It is officially part of week 2. Okay, so one thing I wanted to mention right away is someone in the office hour after class had asked me about the example where we were doing the dy integral for area. And the question was regarding this one, how do we know which function is on the right? And really the best way that I can show this is just by drawing arrows, honestly. So I kind of just go from the right to the left. And as long as I'm on this region, I try to go horizontally right to left and kind of work my way through. And as long as I only have my starting point as this line over here on the right, negative 2y minus 2. And if I move horizontally to the left, I end up on this parabola. Then as long as that's true throughout the entire region, then I'm always going to have the left function be the parabola and the right function be the line. That's kind of what I do. You can do the same thing for the top minus bottom for the dx integrals, but this is kind of how I think about it for dy. I also suggested if you really have a hard time seeing these from right to left versus top to bottom, you can rotate your page counterclockwise 90 degrees. It's got to be counterclockwise. And then your right to left becomes top to bottom. So if you want to see it that way, that's fine. You're still going to have to integrate this with respect to y, but I think it helps you to see at least kind of which function is always on top versus which function is always on the bottom. That just looks clearer. And maybe for different graphs, it's different. But in this particular instance, that would be my suggestion to you. The other thing I was going to mention, I left it upstairs and I cannot possibly go get it right now. But another thing I had mentioned in the office hour for someone who asked was like, what would be like a situation where maybe we were given a function that was written as y equals, but we were supposed to use a dy integral. And one of the cases that I mentioned in the office hour, I pulled this off a sheet I have upstairs, so that's why I don't have it right now. But it was something like y equals the square root of x. And then the other graph, hold on, let me refocus this. I think it's a focus problem. We'll find out. Okay. So y equals the square root of x. And then I want to say the other function was some line. Like maybe let's say it was y equals x minus 4. So the graph went kind of like that. Now, for a case like this, and we were looking above the x-axis, I don't remember what the exact function was, but I'm using y equals x minus 4. And this was only for the case that we were in quadrant 1. So the functions were given to you in y equals, but this would definitely be a scenario where you want to rewrite these in x equals. No, you don't have to. It's not wrong if you don't. You could still integrate this and find the area, but you'd have to set up 2 integrals to do so, because notice that your top function, even though the top is the same all the time, the bottom function would change at 4. So this piece on the left, you would actually integrate normally the way you would have in Calc 1. This would just be your typical, like, find the area under a curve problem, because you're just looking at the area between the x-axis and the curve. And then once you moved on to the right, well, this would be the new stuff over here. So from 4 up into the intersection point, your bottom is no longer the x-axis. It's now this line, x minus 4. So yes, technically you could set it up as 2 integrals. You could go from 0 to 4 of the square root of x, and then add that to the integral. And like I said, I just kind of made this up on the fly. I'm not sure what the intersection point is, but 4 to whatever, and then you would take the square root of x minus the quantity x minus 4 in your other integral. Now, you could do that. What I was saying, though, is it would be easier to do this one using a dy. And the reason it's easier using dy is because the right function is always going to be the same all the time. The right function is always going to be y equals x minus 4, or I should say x equals y plus 4. And then the function that would be on the left then would always be this radical function, which is actually x equals y squared when you square both sides. And if you have a hard time seeing this as the left, and I think that's part of the issue here, is students are having a hard time seeing this as the left because it doesn't seem left, it seems like top. But it is indeed left. You move left and you're going to hit it regardless, as long as you're following a horizontal path. But again, this would be a situation where if you're not sure, rotate it counterclockwise 90 degrees. And when you do that and you think about right minus left as in terms of top minus bottom, I think it's a lot easier to see. So if you want to just do that to sort of help you visualize what's going on, if you're having a hard time seeing the right minus left situation, then maybe do your flip counterclockwise 90 degrees and try to look at it this way. But notice how if you're doing right minus left, I'm looking at it flipped right now, of course, but your right function you can now clearly see is always going to be this line, whereas your left function, which is currently the bottom function, is going to be the parabola. So you could do it either way. One of them just requires 2 integrals, the other requires 1. That's it. Now, moving on, we're going to talk about volume. And like I said, we're really going to be focusing on volume. I'm going to be doing that here and now when we're talking about, let's see, it's technically called disks and washers. Might as well write that down. This is going to be your first section on volume for disks and washers. We're going to talk about shells in 6.3 on Wednesday during your in-class lecture. Don't forget, you're going to have a quiz Wednesday that's going to cover 6.1 and 6.2. It's going to be kind of short. It's mostly going to be questions on setup because, I mean, well, it's kind of easy to quiz you on setup in this section because so much of what is important is in the setup. But don't expect me to be asking you to, find all these crazy integrals. It's mostly just going to be like questions about the setup because it can't be too long. It's probably going to be 15 minutes, but can't be too long. So the shell method that we're going to talk about Wednesday is going to be an alternative to the disks and washer method from today. Now, you're going to find that some of these functions can be done using either method, and some of the functions pretty much at this point have to be done using one method or another just because of the way that you'd have to integrate them. You guys don't have a ton of integration techniques at your disposal at this point. So there might be an instance where you think, oh, I'm going to use a disk on this or maybe a shell on that, and you can't. So you're going to need to learn what's appropriate when. The big difference here, though, is that at least when you're working within a method, you can't just flip your dx and dy willy-nilly. Everything is going to be dependent on the axis about which you're rotating your figure. So let me give you a formula here to start out. This is 6.2, volume of a solid of revolution, disks and washers. Now, disks and washers are technically both within the same method. Shells in 6.3, that's a different method. But disks and washers fall within the same method. Whether you're looking at a disk or a washer just depends on the function that you're given and the axis about which you're rotating that function. And I'm going to be giving you several examples here of disks rotated about the x-axis or the y-axis. Then we're going to rotate them around different axes. Then we'll talk about washers. We'll flip the axes there. And then at the end, I'm going to give you an example where I give you the same function, but we're going to switch the details around. We'll do like 4 different things to it, and you can see how the integral changes. And personally, I think that's one of the most instructive examples to kind of tie everything together in the end. Oh, you guys, I really love this stuff. I'm so excited right now. It's like midnight and I'm jazzed. I was going to go to bed. It's like, oh man, I'm tired. But then I realized I made this entire giant smoothie and it wouldn't be good in the morning. And I was like, you know, got discs and washers I could do. So we're doing this now. Oh, I love this. I love this stuff. Okay. Anyway, very excited. Let me give you a formula. By the way, I've been teaching Calc 2 for several years, and I learned to do disks and washers using functions written as R because they really pertain to radii. So your book, and I hate to deviate from your book. I try to follow exactly what your book does. Your book uses F and G instead of big R and little r. And if you want to use those formulas, you can. That's the only thing that's going to be different about them. Part of the reason I use big R and little r is because that's what I've always done, and it's just what I default to, and I can't make myself revert back. It's very difficult. But I think part of the reason I can't revert to using F and G is because it's so intuitive to me to use big R and little r. So I'm hoping that what I find to be extremely intuitive, you will also find to be so. And that you won't mind the fact that I'm switching up your notation a little bit. I think it's helpful. Otherwise, I would have switched it a long time ago if I didn't think it was good. Okay, to find the volume of a solid of revolution, and I'm going to show you a picture here in a minute so you get a good idea of what's happening. Because you might be like, what are you talking about, volume of a solid of revolution? To find the volume of a solid of revolution, with the disk method, use one of these. Now, which one you use is going to depend on whether your axis of revolution is horizontal or vertical. So I'm going to write down the first one as being for the horizontal axis of revolution. Now, sometimes when I go through examples, I'm going to abbreviate this, and I might write something like horizontal axis of revolution, just because it's a lot to write, and it is very, very important. It's a key point in doing these problems. If you screw up the formula here for dx or dy, the whole problem's going to be wrong. And I've seen students screw this up a lot. They just, I don't know, forget which one goes with which. Okay, the volume is equal to the integral from a to b. You know, I forgot one of the most important things. There's a pi in front of your integral. Pi times the integral from a to b of. And what you're going to do here is you're going to take the radius. It's a function of x. And you're going to square that function, whatever it is. And then you're going to integrate with respect to x. So a horizontal axis of revolution gets a dx integral if you're using disks and washers. Vertical axis of revolution man, I'm running into my camera again. I hate that feeling that I can't move my hand any further to write. Let's see if I can scooch this. Maybe. Okay. All right, so for vertical axis of revolution, very similar. With this one, we just have the volume being pi times the integral from c to d. So normally when we use c to d in our notation, that denotes a dy integral. Now, when you have a dy on your integral, your function needs to be written in terms of y. So this is a radius function written in terms of y. That means that your equation is x equals some function of y, okay? And then here your equation would be y equals some function of x. It doesn't have to be like, but this is the form of your equation. So y equals some function of x, or x equals some function of y. Okay, now if you're wondering, like, okay, what the heck, where did this formula come from? Your book does have some really nice pictures. I pulled out several calc books. I have so many. I have so many at my house, partly because I was on the textbook selection committee and we had to review all the textbooks. And then during that semester, I don't know what happened, COVID hit or I had a baby or something, and I ended up just having all the books and they never asked for them back, and oh well. I have an excessive amount of them. I'm going to flip this. Hold on. So I kind of leaf through them to see which ones have good stuff in them. And your book has awesome pictures. So this is from your book. I'm looking currently at page 436. This is the beginning of section 6.2. But you can see here, and this, by the way, is a horizontal axis of revolution. Sorry, I'm looking at this upside down right now, so I'm going to try to say this correctly. So you have this function, y equals f of x. You're going to revolve it, and in this particular case about the x-axis, we're going to switch our axis of revolution as we work our way through here, but we're going to start out on the x-axis. But this is a basic example of, you know, a standard horizontal axis of revolution, in this case being the x-axis. You've got this function y equals f of x. You're looking at this piece from A to B. And what happens is you're imagining here, and some of you will be able to visualize this better than others. It's just some of us have that skill. You're rotating this around the axis. So you're taking this figure and you're kind of spinning it around the x-axis. And as you spin it around the axis, it's going to generate this solid that you're seeing in this picture for B. So you're spinning it around, and it's going to generate this solid of revolution. When we talk about washers in a minute, you guys know what washers are. They are like circles with holes in them. This one doesn't have a hole. This is why it's a disc. We're taking something that's solid. It meets the axis of revolution everywhere. When we spin it around, it creates a solid figure with no holes in it. That's why we call this a disc. But the way that you're looking at this in terms of calculus is you're thinking about this height of your disc as being some radius. And that's, in this case, your radius being some function r of x. And whatever that radius is, the width of your disc is delta x. And that's the piece that goes into your integral Where is it? Sorry, I'm upside down. Yikes. Oh, you know what? Maybe it's on the next page. Maybe I was looking at this in a different book where they pieced it together. Oh, well, either way, it's still a beautiful photo and you can still tie it together with your formula. But this is the thickness of the disc. And you can see now if you run this around this disc and it goes from A to B, you can make this thickness as narrow or as thick as you'd like. That's where the width of that rectangle comes in. You're going to be able to generate a volume kind of depending on where this rectangle is placed. And that's sort of how you build this integral. Let's see, the picture on the next page is similar, same idea. This would be on page 437. But you can kind of see here, same idea. This one I like a little bit better because it sort of builds up this disk as you work your way through. So here's the function y equals the square root of x. And here's that disk you're looking at. So, well, technically you see the disk here, but you're building the disk off this rectangle. The height of your rectangle is also representing, in this case, the radius of your disk. So depending on where you move this rectangle, your radius could be down here, your radius will be less, down to 0, or your radius could be as high as the square root of 5 if you move it all the way here to the right. So that's going to vary depending on the particular positioning of where that's placed. But you can see you roll this disc around and you create this figure that you're seeing here for your solid of revolution. That's what a solid of revolution is. This was a particular example from the book, but I thought the picture was nice. So therefore, we looked at it. And I bet you have a nice one for a dy integral too. I mean, I think you kind of get the picture at this point, but actually, they don't have a nice one for a dy for a disk. Oh, no, they do. They do. I accidentally missed the page, that's all. So if you look at page 439, ooh, this thing is heavy. Okay, this way. You can see how something similar is done if you instead revolve about a vertical axis of revolution. So same idea, but this time the radius would be still the height of the rectangle, but the height of the rectangle is dependent on this function. And we're going to be thinking about this the same way we did with area. You're going to be thinking right minus left. So in this case, you're taking your function, which is g of y, and subtracting off the left. Well, the left is just x equals 0. So that's really going to come into play when we talk about washers. But be thinking about that as you work your way through. Just thinking about, okay, if I'm dealing with a vertical axis of revolution, I'm looking at right minus left. You're generating then this disk, and then that generates your solid of revolution. Okay, so I feel like we saw a lot of pictures. So hopefully you're getting a sense for what's going on. I do think I'm going to graph each one of these for each example, because you know I love to graph anyway. So I'm going to graph these, but I think it's usually pretty easy to get a visual on these, especially the disks. Okay. The hardest part about any of these volume things in 6.2 is just making sure that you find the correct radius. So that's really what I'm going to be focusing on here. And that's where the setup is going to be huge for you. I'm not worried about like, can you integrate? I'm worried about like, can you set it up properly? That's going to be the trick. Okay. So yeah, let's do it up. Example 1. Find the volume of the solid formed by revolving the region bounded by the graph of y equals 3x, y equals 0. I should have said the graphs of, because I'm technically giving you more than one equation. The graphs of y equals 3x, y equals 0, x equals 1, and x equals 3 about the x-axis. So let's go ahead and graph this so we have a good sense for what's going on here. All right, y equals 3x. So that means the slope is 3, the y-intercept is 0. 1, 2, 3, up 3 over 1. 1, 2, 3, up 3 over 1. My scale's a little off here. That'll be 6, 3, and we will do one more. 1, 2, 3, up right over 1. So something like that. So there's y equals 3x. If you'd like, you can also graph it down here, but notice that we're binding this by y equals 3x, y equals 0, which is the x-axis. So we actually don't need to worry about any part of this graph that goes down and to the left. So if you want to just pop it on there, because technically it exists, that's fine. Okay, so y equals 0 is the x-axis. Then we have x equals 1 and x equals 3. So there's this point at 1, 3. And there's a point at 3, 9. And again, if you're not sure, you can always plug those in if, you know, if x equals 3, y equals 3 times 3, which is 9. All right, so we have that. So we are looking at this region between 1 and 3, and between y equals 0 and y equals 3x. Now we are revolving this about the x-axis. I would show that if I were you with some sort of arrow so that you know and that you're thinking about it. It's really important to think about. Now, I would strongly suggest that you draw a rectangle to represent the radius of the disk that we're going to be spinning around, or the disk that's going to be created as we spin this thing around. So it doesn't really matter what the thickness is, but the rectangle that you draw is always going to be perpendicular to the axis of revolution. And I think that, like I said, you don't have to draw this, but I really think that drawing this rectangle is going to be helpful just to help you figure out exactly what the radius is. Yeah, I just thought of something. Hold on, let me. Okay, nope, we're good. Okay. So the radius, by the way, is just going to be dictated by whatever the height of the rectangle is. So, I mean, you're looking at this right now from a side view, but I mean, if you think about what this figure is actually going to look like as it gets rotated through, it's basically going to be this thing, kind of like that, if you were to look at it from the side. But if you were to spin yourself around and stand here at the end of the x-axis and stare at it, all you would see would be a circle, because you're just taking this and spinning it around. And it would just be a circle if you looked at it from, I keep wanting to say the top, even though it's technically looks like the left. But I mean, essentially it kind of is just this thing that looks like that, if that helps you to to get a visual. All right, so you're spinning it around. Technically, it only has to spin around once, and then you create this shape. There's no hole in the middle. It's a solid disc. So if you're wondering, like, wait a second, I think I know where this formula came from. Pi r squared is the area of a circle. If pi r squared is the area of the circle, then all you're doing is taking this circle and then multiplying it by just the width of this rectangle as you work your way through from A to B. It's kind of where that comes from. Okay. So the radius in this case, the height of your rectangle is just going to be dictated by this function, y equals 3x. So depending on where you are, the radius is going to change. So let's say you were sitting here at x equals 1. Well, the radius is 3x. I'm going to write that down, actually. I always recommend kind of checking these and eyeballing it and make sure that your radius makes sense. If you're sitting here at x equals 1, then that means your radius should be 3 times x, which is 3 times 1, which is 3, which indeed it is. You would be able to see that you would have a radius of 3 here. But if you were sitting here at x equals 3, well, your radius is 3 times 3, your radius would be 9. That makes sense. You're going all the way up to 9. So the radius would be 9 here. So it kind of depends on where you are, but I would just do a double check of the radius function that you're writing, make sure that it makes sense, which this one does. This is a really straightforward disk. So if you're wondering like, well, this didn't seem confusing, what's so bad about that? This is not supposed to be one of the like super hard ones. It's example number 1. Okay. So your radius is 3x. Now, double check, because you want to make sure that we're using the right variable. We have a horizontal axis of revolution. When we have a horizontal axis of revolution, we do indeed want a dx integral with r of x, not r of y. So just double check, make sure. And if we're looking at a dx integral, then I'm going to be looking at x limits of integration as I move from left to right. So my volume here is going to be pi times the integral from 1 to 3 of the quantity 3x squared dx. Now remember that when you square a quantity, you need to multiply it by itself. So this is really 3x times 3x, which is 9x squared dx. The parentheses are non-essential, but you know, I'm kind of like a robot when it comes to parentheses. If you'd like, you can pull the 9 out. You don't have to. It's up to you. I'm just going to leave it in. So we'll integrate now. We don't have anything else to do here. This is just a monomial. We're going to increase the exponent by 1 and divide by the new exponent, and we'll take that from 1 to 3. So this is really pi times 3x cubed from 1 to 3. And then, if you want to take out the 3, that's fine. I'm going to leave it in. 3 times 3 cubed minus 3 times 1 cubed. And then we'll simplify. 3 cubed is 27 times 3 is 81. And then you have 3 for the second term, and that leaves you with 78 pi. There's really not a good way to check something like this. The only suggestion I usually give students for how to check volume problems is once you learn the shell method, do the problem 2 different ways. And that works on a lot of them, but not all of them. And then sometimes you'll miss one thing and then you'll get different answers. And even though it technically should have been right, it doesn't look right. So even though we do have ways to sort of double check ourselves, it's not necessarily the easiest thing to do. But we know a couple of things, like, I mean, we know our answer shouldn't be negative because you can't have negative volume. So something like that definitely would be a clue that something didn't go well. Other than that, you know, make sure you have the pi on your answer. Okay. Let's do another example, and this time we're going to switch our axis of revolution. Okay, example 2. Find the volume when y equals x squared plus 3 is revolved about the line y equals 2, and our figure is going to be bounded by x equals -1, x equals 2, and y equals 2. The picture here is going to be crucial. I suggest graphing all of these, and I would do it by hand if I were you. I can't make you do it, but I think it's really going to help you determine your radii. So y equals x squared plus 3 is your standard parabola shifted up 3 units. So there's the vertex. And you've got this point now at 1, 4, -1, 4, and then we're going to go up 1, 2, 3, 1, 2, 3, 4. So you'll have points here at 7, I'm sorry, 2, 7, and -2, 7. And you don't need to have everything exact here because really we're just going to be focusing on just what is the radius. So this is y equals x squared plus 3. We were binding this by x equals -1. Sorry, my point is like a little bit too far to the left. Should just move it so it doesn't look like I'm using a different point. I'm also at a weird angle, so in my defense. X equals 2. Okay, so our region is bounded by this parabola, x equals -1, x equals 2. Remember, x equals always represents vertical lines, and y equals 2. Now we're also revolving this about the line y equals 2. So it doesn't actually exist on the graph, so I'm going to leave it dashed. But that'll be y equals 2. And I'm looking for the region that's bounded between these 4 equations or graphs, if you want to say that. So this is the area of the region I'm looking at. And sometimes that's even the hard part, is just picking the right area. You'd be surprised what kind of crazy things students will do. I'm sure I did crazy things as a student too. It's true. Okay, but we're going to be revolving this about the line y equals 2. So it's still a horizontal axis of revolution. So you might want to note that because we're looking at a horizontal axis of revolution, we're going to go from a to b of r of x squared dx. If you want, just make a note, or even if you want to make a smaller note to yourself, you can just say horizontal axis of revolution, and then say dx integral, find r of x, something like that, so you know. feel like I just swallowed a bug or something, but I don't know. Maybe now you're going to go back and rewind it and be like, did she swallow a bug? But I don't think anything was flying around. Okay. Let me tell you, there's nothing worse than swallowing a bug, especially if you're having a nice, like, cool evening run. You're running down the street and all of a sudden this bug flies into your mouth. Oh, it's disgusting. You guys, I can't even. So gross. Terrible. Terrible. Oh. Anyway. I don't know. Has anyone had that experience or is it just me? Terrible. Okay. Let's talk about finding the height, or I should say the radius. Sometimes I call it the height because I think that's also sort of an intuitive way of thinking about this. But I'm looking at the radius of this figure. I'm always going to draw my rectangle when we're talking about disks perpendicular to the axis of revolution. So my rectangle, I'm just going to represent it right there. If you're wondering why'd she put it there, it doesn't matter where you put it. You just want to have a rectangle perpendicular to your axis of revolution so you can get a good idea of how to represent the height using a function of x. Now, here's where our discussion of area is going to come into play. So when we're looking for r of x, you're thinking about this in terms of top minus bottom. The reason I can't say r of x is x squared plus 3 is because that doesn't check out. If I let my radius be x squared plus 3, well, let's say then I'm looking for the radius of this figure at x equals 0. If x equals 0, then my radius should be 0 squared plus 3. My radius should be 3. But I'm not revolving this about the x-axis. I'm revolving it around y equals 2. If x equals 0, my radius should only be 1 unit. So you should be thinking about this in terms of top minus bottom. You're going to take off that axis of revolution wherever it happens to be. So you're taking the function x squared plus 3 and then subtracting off 2. That's your bottom. So y equals x squared plus 3 minus y equals 2. So if you want to think about this as top minus bottom, I know it's sort of rudimentary and horrible notation, but personally, I feel that that makes sense. So your top function minus your bottom function, that's actually the area that you're covering there. And remember, we're talking about the area of the disk so that we can then find the volume of the disk. And then you're going to simplify this. So this is going to become r of x equals x squared plus 1. Now I'm going to put a box around that because it's such an important conclusion. And then this, again, you can check this. If you let x be 0, your radius is 1, which indeed it should be, because between your axis of revolution and your top of your figure, you're at 1 unit. Let's say we let x be 2. Well, we're expecting the radius to go, I don't know, up to however many units. What point was I at here? 2, 7. So I'm expecting the radius to be 5. And indeed, if I let x be 2, 2 squared plus 1 is 5. So I'm covering the 5 unit distance from the axis of revolution all the way up to this point if I let x be 2. So that's what I mean just by checking it. Some of you might be wondering, like, well, what if the axis of revolution was y equals -2? You would do the same thing. It's just that in that case, you would be taking minus -2 and you'd actually be adding 2 to the function. I'm even going to write this down. If the axis of revolution was y equals -2, then you would have r of x equals x squared plus 3 plus 2. which is x squared plus 3 minus -2. You would still be taking top minus bottom. I do feel, though, that that would be slightly more intuitive just because you would be covering the whole distance to the x-axis, and then you'd be covering 2 more units. I mean, assuming that I bound you at -2 instead of +2. Otherwise, you'd have a washer. Look at that. I'm trying to be more helpful, and then I ended up opening up a can of worms. Assuming the lower bound was y equals -2. Okay. So that would be the case. So I'd be taking this whole area from 0 to the function and then adding 2 more to it. And again, I'm going to go through an example at the end where we're doing all kinds of crazy things and switching things around. But just because I thought some of you might be thinking it. Okay. All right, so we have the radius, and this is a disk. I mean, if you think about the fact that you're spinning this around the line y equals 2, I mean, it's going to be touching at every point. There's no hole in it. And if you looked at it straight down this line, it would just look like a circle. And well, technically you can have a washer that looks like a circle, but we are flush up against the axis of revolution at every single point. And that's really what signifies a disk. All right, so let's go ahead and set up our volume integral. This is pi times the integral from -1 to 2, because these are my my limits here, left and right. And then I'm going to take my radius and square it. Maybe I should have done that separately, but forgot to. So my r of x is x squared plus 1, and that quantity is going to get squared, and then we'll integrate with respect to x. Remember, when you're squaring a quantity, you are not going to distribute the exponent. This is not going to become x to the 4th plus 1. You must actually FOIL it out. So multiply it by itself. And then we'll have pi times the integral from -1 to 2 of x to the 4th, and then plus 2x squared plus 1 dx. And now you can integrate and use the FTC. So 1/5 x to the 5th plus 2/3 x cubed plus x. And you can go from -1 to 2. And you feel free to pop this into your calculator. 2 to the 5th is 32. So 32/5, 2 cubed is 8, times 2 is 16. And then plus 2, and then subtract off the evaluation at -1. -1 to the 5th is going to be -1. Then we'll have minus 2/3 minus 1. Oh my gosh, I got everything I needed in this world and not a calculator. Oh, I was just saying in the office hour how I have 3 of them, but they're never all where I need them. Oh my goodness. Oh, I have to go get it. I'm going to need it. Why didn't I get my calculator? Okay. I'll be right back. Sorry about that. All right, 32/5. I'll do this with you, or maybe not. Let's see. 32/5 plus 16/3 plus 2 plus 1/5 plus 2/3 plus 1. Moment of truth. 78/5 pi. Actually, I didn't even think to tell you that on the last one. We're going to leave our answers here exact, written in terms of pi. So don't multiply the pi in and give me a weird decimal approximation. Leave it exact. Just remember that the pi goes onto it as a multiple. Okay. Now, my goal here today is to give you examples that illustrate a couple different types of pictures so that you'll get some experience looking at each type. And that's really what I want you to see in example 3. Example 3. Find the volume of the solid revolved about the line y equals 4 bounded by y equals x squared minus 2x plus 1, x equals 0, and y equals 4. Second time I've done that today. Okay, so let's graph this out. This is actually a perfect square trinomial already. If you recognize that, awesome. This is just x minus 1 quantity squared. Remember, you're looking for half of the middle term squared, and it's already added on. So half of -2 is -1. Square it, and you get +1. That tells you that you're looking at a perfect square trinomial. You don't need to know that except if you're going to graph it. This means that you're looking at a standard parabola shifted right 1 unit. Because remember, the minus sign is in the parentheses. That means we're shifting to the right. This is right for you. So I'm going to go ahead, start to graph this. Standard parabola shifted right 1 unit means the vertex is going to be sitting here at 1, 0. And I've got these points, one up and left and up and right in each direction. Then I've got a point at -1, 4. And I've got a point at 3, 4. And again, you could use a table of values to graph this if you prefer. So it looks something like this. Don't forget that we're also binding this by x equals 0, which is the y-axis, and y equals 4. And we're revolving this about the line y equals 4. But if we're binding this by our parabola and the line x equals 0, x equals 0 is the y-axis. So I'm looking at this region. Okay. Now we have a horizontal axis of revolution. When you have a horizontal axis of revolution, that means you're looking at a dx integral. So I'm going to need a radius written in terms of x, and I'm going to need a dx. Okay, so I'm going to go ahead and draw my rectangle, put it wherever you want. It's perpendicular to the axis of revolution. So it looks like that. Now, I have a feeling you might be tempted to say, Well, isn't the radius just y equals x squared minus 2x plus 1? Be careful. Think back to what you know about area. We spent so long talking about it tonight. If we're thinking about top minus bottom, then no, you would not have a radius of r of x equals x squared minus 2x plus 1. Think about this in terms of top minus bottom. The top function is y equals 4. The bottom function is your parabola, y equals x squared minus 2x plus 1. Remember to put parentheses around this because you are subtracting off this entire quantity from 4. We're going to check this when we're done, by the way, or at least check your radius just to verify that it makes sense. So we'll have negative x squared plus 2x plus 3. So if you were trying to figure out, if I was revolving this around the line y equals 4, what would the radius be at x equals 0? So at x equals 0, I'm expecting the radius to be 3 because I'm covering from my axis of revolution this whole distance from the center to the outermost point, which looks like 3 units exactly. So test it out. Look for r of 0. R of 0 is indeed 3. Check. If you want to test it out again, you could maybe test out r of 3. You would be expecting the radius here to be 0 because there's actually no distance covered at this point. This is where they intersect. So you wouldn't actually have anything left to your figure. So r of 3 would be negative 9 plus 6 plus 3, which is indeed 0. You don't have to check all of these. I would recommend checking the ones especially that you're not sure about. Anytime we move the axis of revolution, I feel like there needs to be more checking going on. Okay. All right, but now we're good to go because now we know our radius function. Actually, we're kind of good to go. Remember that we have to square the radius function, and this is a trinomial. But that's fine. No big deal. It's all good. Okay, so we're going to take negative x squared plus 2x plus 3 and multiply it by itself to get r of x squared. I'm just going to distribute into, I'm going to use the first term and go into every term. And then I'll use the second term, multiply by every term, and the third term, multiply by every term. So negative x squared times negative x squared is positive x to the 4th. Then we'll have negative 2x cubed, and then we'll have negative 3x squared. I kind of like to add these up vertically. So as I move my way into the second term, I'm going to focus on doing that. Negative 2x cubed, positive 4x squared, and positive 6x. And then negative 3x squared plus 6x plus 9. We'll add them up. We'll get x to the 4th minus 4x cubed minus 2x squared plus 12x plus 9. Okay. And now we have r of x quantity squared. And go ahead and put that into the integral. So we'll have pi. Oh, sorry, cut you off, but that's okay. I'm going from 0 to 3. That was the value at which we cut this off. And actually, it was just because we graphed it so beautifully that we could tell that was the intersection point. To find the intersection point, you would have just solved the equation x squared minus 2x plus 1 equals 4 to find that intersection. So we're going from 0 to 3 of x to the 4th minus 4x cubed minus 2x squared plus 12x plus 9 dx. and then we'll integrate, and then we'll evaluate the definite integral. So we'll have 1/5 x to the 5th minus 4/4, which is just 1 x to the 4th, minus 2/3 x cubed plus 6 x squared plus 9x. Now, the nice thing is you're looking at a polynomial and your lower limit of integration is 0. If it's a polynomial, you don't need to evaluate it at the lower limit. So I have pi times 3 to the 5th is 243 or 245. 3 to the 5th, 243. 243 fifths minus 3 to the 4th is 81 minus 2/3 times 27 plus 6 times 9 plus 27. Let's see, 243 fifths. Sorry, I'll do this on screen because why not? Minus 81 minus 2/3 times 27 plus 6 times 9 plus 27, moment of truth, 153 thirds pi. Oh, 153 fifths, not thirds. Fifths. Sorry about that. Okay. Awesome. Now let's do one that is revolved about a vertical axis of revolution. So this will be example 4. Find the volume of the region bounded by y equals x cubed, y equals 5, and x equals 0 when revolved about the y-axis. Okay, so this means vertical axis of revolution. And that means we're going from C to D, and we need an R of y squared dy. So I always try to note that right away, just to make it really clear so you don't screw up which variable is supposed to be which. All right, now you might be wondering, like, wait a second, I thought she said this was a dy. Why didn't she give us equations written in terms of x, or I'm sorry, in terms of y as x equals? Well, most of the time you're not going to get that here. You're going to have to do that yourself. But you know how to do that. If y equals x cubed, then x we can isolate by taking the cube root on both sides. So if y equals x cubed, then x is the cube root of y, which is also known as y to the 1/3. So you might not need that right now because what we're going to be doing is graphing, but you'll definitely need it later. Okay. So let's go ahead and graph this region. It's revolved about the y-axis. I'm going to graph this piece first, y equals x cubed. This is your cubic function. It has a point at 0, 0. It has a point at 1, 1. And it has a point at -1, -1. It also has a point at 2, 8. So right about there, if I'm eyeballing that correctly, and -2, -8, which is approximately right there. And we're bound by x equals 0, which is the y-axis, but that's okay. It helps to get a full picture here. There it is. Your Elvis graph. All right. Enough. Y equals x cubed, also known as x equals y to the 1/3. All right, we're also looking at y equals 5. It's also really important. I know it sounds really basic, and I'm not trying to talk down to you. We have to remember that y equals is a horizontal line. X equals is a vertical line. So when you have y equals 5, that's a horizontal line that goes through 5. 1, 2, 3, 4, 5. I mean, I guess if you dash it or if you draw it, I mean, it's technically on here. Technically. Okay. This is y equals 5. And we are taking the region bounded by y equals 5, y equals x cubed, and x equals 0, which is the y-axis. So there's your region. And we're revolving it about the y-axis. So it's doing something like this. Remember that when you're looking at the disk method, we're always going to be drawing our rectangle perpendicular to the axis of revolution. So if you remember that, which is key, I keep saying it on every example, that means you should be doing it. I'm looking at a rectangle that's, in this case, oriented horizontally, perpendicular to the axis of revolution. And now I hope we can start to see where this dy is coming in, because in order to find the radius, I'm looking for the height of this rectangle. And the height of this rectangle is going to be represented by a function, and we're going to figure out what that is by taking right minus left. So r of y is going to be right minus left. Everything has to be written in terms of y. The right function is y to the 1/3. And the left function is 0. So x equals y to the 1/3 all the way up to x equals 0. You don't have to actually write that. I just feel like it's not as intuitive when you're going right to left. So that's why I'm actually showing this and subtracting off 0. So we're going with right minus left. And again, if you want to flip this 90 degrees, you can think of it as top minus bottom. Just keep writing it the way that you're seeing it, with respect to the variables that you are seeing this displayed with. All right, so there's that. I have my r of y. I know this is a disk, not a washer, because it is touching the axis of revolution at every single place. I don't have anywhere it's not touching. Let's go ahead and find r of y squared. Sometimes I do that before I pop it into the integral. Kind of depends. This is y to the 1/3 squared. I guess I should have rewritten that. Remember, when you take a power to a power, you multiply the powers. So y to the 1/3 squared is y to the 1/3 times 2, which is y to the 2/3. And remember, when you're integrating with respect to y, your limits of integration actually lie on the y-axis, not the x-axis. So when you set up your volume integral, you are not going from 0 to 2 or whatever that, you would have to actually find that point. It's not actually at 2. But don't do that, because that's not what you're supposed to do. We are looking for limits of integration, c and d, which lie on the y-axis. So we're going from 0 to 5. Don't make it harder than it has to be. R of y quantity squared dy. So now we're going to integrate. I'm going to add 1 to the power, and I'm going to divide by the new power. When I add 1 to 2/3, well, 2/3 plus 3/3 is 5/3. So I'm going to get 3/5 y to the 5/3. And I'm going to evaluate that from 0 to 5. Now, I know if I evaluate this at 0, it's going to zero out, so I don't need to worry about that in this case. So I'm looking at 3/5 times 5 to the 5/3. I want this to be exact. And if you're confused about like, how could I possibly make this exact? I'm going to show you how you would make this exact right now. By the way, Achieve might accept this as some weird decimal approximation if you had this instance. 5 to the 5/3. Well, first of all, I'm going to rewrite this as 3/5 pi. And then we're going to multiply this by 5 to the 5/3. Remember, oh gosh, sorry. If you have the same base and you're multiplying, you add the exponents. What that means is I could split these up. I could say that this is 5 to the 3/3 times 5 to the 2/3, right? I have the same base and multiplying. I can add the exponents. 3/3 plus 2/3 is 5/3. Well, 3/3 is 1. So 5 to the 3/3 is just 5. And then you have 5 to the 2/3. So it's kind of up to you. I'm going to go ahead and cancel these two 5s out, and that leaves me with 3 pi, and then I have 5 to the 2/3. Honestly, if you got it to this point, I would be fine with it. Whatever you do, don't multiply the 3 and the 5. This is not really 5. I know it looks like 5. It's in disguise, though. This is 5 to the 2/3 power, which is not quite 5. It's less than 5. It's not 5, though, so you can't multiply it by 3. If you wanted, you could even write this as a radical. You don't have to. I would probably just say, leave it. This is fine. Okay, so that was an example where we were looking at a disk such that we had a vertical axis of revolution. All right, so we talked a lot about disks. Let's talk about washers. The washer method. You will find that this is extremely similar to the disk method, except that you're going to have to account for the fact that you don't have a full radius because you're cutting out a piece in the middle that isn't going to count. I'm going to use the same notation here, except that R of X is going to denote the outer radius. It's the big R, and the outer radius is the bigger one. Little r of X is going to denote the inner radius. And I had mentioned before, if you are using your book's notation, they're calling the outer radius f of X and the inner radius g of X. And it is fine if you want to use that notation. I do not have a problem with it. All right, so let's look at the case where we have a horizontal axis of revolution. In that case, your formula is going to change ever so slightly. We're going to take pi times the integral from a to b of r of X, quantity squared, so it looks the same so far, but I have to subtract off the inner radius. The inner radius is where we're going to get the hole that's inside that figure. Now I'm going to get my pictures out again, so we can talk about pictures of washers. Trying to find the best picture. I kind of like this one on page 441. flip this for you. Oh, no, the top one I like better. And it builds it up a little bit. Okay. So like I said, they're using f of x to denote the outer radius and g of x to denote the inner radius. So if you're thinking about this in terms of disks, well, in this case, if your two functions are above whatever your axis of revolution is, or they're off that axis, then you're going to end up with a piece in the middle. So you can see how you're taking this region right here, and it's being rotated about the x-axis. Well, as you're spinning this around, it's creating a figure, but the figure looks like this, what you're seeing in part C of this figure. Because as you're generating this around, there's all this space underneath g of x that's not actually part of the figure. And since you're rotating this about the x-axis, well, all this space that's not part of your figure is empty. And that's where you're getting the washer situation. Now, it's obviously changing its shape over the course of the revolution, just because of the fact that these particular functions are not straight horizontal lines. They're functions of x. So that's why you're getting this curved shape to the function. But it's really important to recognize that because you don't have a situation where your region is flush up against the axis of revolution, that's where you're getting the situation where the washer is created. So in the situation where we have a disk, your region would go all the way down to the axis of revolution and it would touch it at every point. Now with a washer, this particular example shows a washer that it has like a real actual hole in the middle. But there are cases of washers where it's not necessarily like a hole in the middle. It's just that it doesn't touch everywhere. So an instance of this would be where you have this vertical axis of revolution on page 443. Let's see, this way. Oh, this is very hard to do. Let me see if I can raise that. I have to switch my Zoom all over again. That's okay. I'll do it for you guys. Here are the graphs. And you can see here that these two create a whole bunch of space between the axis of revolution and the actual region itself. So as you spin this around, notice that you could still stare right down the y-axis and it would look like a circle to you. The only thing you would see would be this top part. Even though there's going to be a hole in it, you wouldn't see that because it does eventually meet at the bottom. So just because you can't see through it doesn't mean it's not a washer. What you're looking for is a situation where it's not completely flush up against the axis of revolution everywhere. It only touches in this case at 0, 0. So in order for it to be a disk, it has to touch everywhere. For it to be a washer, there needs to be at least one place where it doesn't touch. So I hope that makes it a little bit more clear. But as I go through these washer examples, I have 2 washer examples, and then I want to give you like the combo example. I want to make sure that we draw these out and get a good sense of what's actually happening with the region as you rotate it about. Gosh, these books are so heavy. They're huge. Oh. Okay. I'm going to rotate back. Okay. Where am I here? Scoop this other way. All right. So that would be a situation where you have a horizontal axis of revolution. You'd be using this formula. For a vertical axis of revolution, I mean, same idea. You can figure out what the formula would look like, but you're going from C to D, and you're going to take R of Y, quantity squared, and subtract off little r of Y, quantity squared. So my goal in the next couple of examples is to really help you figure out, first of all, do I have a disk or do I have a washer? Second of all, if I have a disk or a washer, what's my radius? What are my radii if I have a washer? So we'll look at these. Example 5. Find the volume of the region bounded by y equals 1 over x equals 1, x equals 3, y equals 0, revolved about the line y equals 2. All right, so let's graph this out. Y equals 1 over x. This is your reciprocal function. If you don't remember what it looks like, I feel like this one's pretty easy to graph just by plugging in values. If x is 1, y is 1. If x is 2, y is a half. You'll see this kind of go so on and so forth. If x is 3, y is a third. If x is a half, y is 2, so on and so forth. So your reciprocal function does something like this. And it is an odd function. It repeats itself on the other side. You don't actually have to graph this because it has nothing to do with what our instructions are dictating. But this is your reciprocal function, y equals 1 over x. So it technically includes 2 branches. Then we're looking at x equals 1, x equals 3. So these vertical lines. And y equals 0, which is the x-axis. And we're revolving this about the line. Oh, I guess we should fill in our region first. All right, so we're going from 1 to 3. We're revolving this about y equals 2. Y equals 2 is a horizontal line. Okay, now not only does our figure not even touch the axis of revolution, well, actually, I was going to say not only is it not flush up against the axis of revolution, but it doesn't touch it anywhere. So if you are not even touching the axis of revolution at all with your figure, then it's a washer. If you're not touching it everywhere with your region, it's a washer. Now, if I was revolving this about the line y equals 0 or the x-axis, then it would be a disk. If revolved about the x-axis, it would be a disk. Because notice that if it was revolved about the x-axis, I would still have this horizontal axis of revolution. But in this case, at every single point from 1 to 3 in this region, I would be touching the axis of revolution. But that's not the case with y equals 2. So we're going to revolve this about the line y equals 2, and it's going to create this, identical figure above it. Going to look kind of like that as it goes around and around and around. Now, from the side, of course, this would just look like a rectangle. But if you looked down the region from this line y equals 2, it would look circular, except there would be a hole in it. So it kind of goes like that. And of course, you're not going to see those pieces. So we definitely have a washer. So when you have a washer, you have two things you got to get right: the outer radius and the inner radius. So remember it, and if you're one of those people who just kind of needs to visualize instead of thinking about like formulas or top minus bottom or something like that, that's fine. You can look at the outer radius by going from the outer edge of the figure, which is this edge on sitting on the x-axis, and then take that radius all the way up to the axis of revolution. Now, I drew the arrow like this because I'm thinking about this in terms of top minus bottom. But you do what you want to do. You do you. I think the outer radius in this case is much easier to see because it's going to be 2 all the time. The distance between the axis of revolution and the outer edge of this figure is always going to be 2. It can't help it. It has nothing else that it can possibly be. It's going to be 2 all the time. And it's a horizontal axis of revolution, so it's an r of x. Now, it can be constant. That's fine. No big deal. If you're thinking about this in terms of top minus bottom, well, the top is going to be your axis of revolution, which is 2. And the bottom is going to be the y-axis, which is y equals 0. So you would think about it as 2 minus 0 if you were thinking about the outer radius as being top minus bottom. I always have this paranoia that I'm recording and I'm not like sharing my screen, or my microphone's broken, or I forgot to hit record. I'm constantly like double checking. Okay. Now for the inner radius, you're going to do something similar, except instead of going from the axis of revolution to the outer edge of the figure, you're going to go from the axis of revolution to the inner edge of the figure. So that would be little r of x. So that one's little r. That one would be big R. The other one I drew the arrow for. But little r you can also find by going top minus bottom. This time, though, the top is 2. The bottom is 1 minus x. Or I'm sorry, 1 over x, not 1 minus x. So my top is still going to be 2. My bottom is 1 over x. And again, this is something that you can kind of check, not completely and fully, but here the outer radius is 2 all the time. I think you can eyeball that one. But think about what happens at 1. If x equals 1, the inner radius just goes from the axis of revolution to this inner edge of your figure, which is 1 unit. Well, 2 minus 1 over 1 is 2 minus 1, which is 1, which is indeed the radius from the axis of revolution to the inner edge of your figure. It's a little bit harder to check as you move your way over to 3, just because these numbers are going to be fractions, but you can still tell that your inner radius would be getting larger because you're subtracting off a number that's smaller. Okay, so now we have r of x and we have little r of x. Remember, though, that our formula dictates that we must square them. Sometimes we spend so long finding the radii that we forget to square them. We just get carried away. So let's do that. I'm not worried about squaring big R of x. Big R of x is just 2 squared, which is 4. It's little r of x, and I'm not even really worried about it. I'm just thinking that, we don't want to forget about it. 2 minus 1 over x times itself is 4, minus 2 over x. Minus 2 over x is minus 4 over x. And then plus 1 over x squared when you multiply the last terms together. Now that we have big R squared and little r squared, we'll go ahead and set up our volume integral. So we're taking pi times the integral from, and because we're looking at a dx integral, I need x limits of integration. I'm going from 1 to 3. Sorry, this figure got to be looking really messy, didn't it? And I'm taking r squared, big R squared, minus little r squared, which is this whole quantity. 4 minus 4 over x, I'll leave that one, plus, and instead of writing 1 over x squared, I might just write it as x to the negative second. I know I'm going to have to integrate it. Right, like that. And then we'll simplify before we integrate. So this is pi times the integral from 1 to 3, 4 minus 4. Your constants are gone. But you're still going to distribute this negative sign in. So you'll have positive 4 over x minus x to the negative second dx. If you're wondering, like, wait a second, why did she write this as x to the negative second, but she didn't write this as x to the negative first? Well, remember that I can't use the power rule when I just have x in the denominator. This is in the form of a natural logarithm. So I'm just going to have to keep it like this and integrate it the way that it is. So I'll have 4 times the natural log of the absolute value of x. Technically, you're only going from 1 to 3, so the absolute value bars you can drop in this case. And then I have negative x to the negative first divided by negative 1. We'll simplify that. So you see we have pi times 4 ln x plus 1 over x, and we'll go from 1 to 3. So I have 4 ln 3 plus 1/3 minus 4 ln 1 minus 1. Now ln 1 is 0. If you don't remember that, get used to that. The natural log of 1 is 0. You can always check that in your calculator, but that's a result that you're going to use pretty often. We have pi times 4 ln 3. Leave it exact. Don't give me a decimal approximation. Positive 1/3 and negative 1 will give you negative 2/3. And that is the exact value for your volume. Oh, the smoothie is gone. I guess that means it's time to go to bed. Just kidding. I still have 2 more examples to go over. I'm not going to gyp you guys just because my smoothie's gone. All right, so let's do another washer. Of course, this one is going to be a vertical axis of revolution. And then we'll put it all together. Example 6, find the volume of the region bounded by y equals x squared, x equals 0, y equals 4, revolved about the line x equals 3. I keep pausing like I'm giving you guys time to write this, but technically you're watching the video. You can pause it on your own. It's a habit. All right, y equals x squared. I'm only going from, or I'm revolving this about x equals 3. And I'm looking at this between 0 and y equals 4. So x equals 0 is the y-axis. So I only need to graph the right-hand side of this. Now this is the point 2, 4. And notice, by the way, that I'm revolving this about the x-axis. I'm sorry, about x equals 3, not the x-axis. This is the vertical axis of revolution. You know what I think part of the problem is? students see x equals and they automatically think horizontal because the x-axis is horizontal. You have to remember that an x equals is a vertical line. That's a vertical axis of revolution. If we have a vertical axis of revolution, that means that we're of the form, oh gosh, I need to write this as a washer. Technically, you don't know it's a washer yet, but r of y squared minus little r of y squared dy. Lots of grouping symbols there. Possibly one too many. Oh no, maybe not. Maybe they just look funny. One too few. All right. So that's what I'm looking for here for the vertical axis of revolution. Here's y equals x squared. X equals 0 is the y-axis. I am also binding this by y equals 4, which is the horizontal line that goes through y equals 4. All right, so there's my figure. I'm revolving this about x equals 3. So notice that if I revolve this about x equals 2, I would still have a washer because I only would touch the axis of revolution at one point. But I'm not even doing that. I'm moving this over to 3. And then I'm revolving it about this axis. So the fact that my figure doesn't even touch this at all, it's a dead giveaway that this is a washer. You must touch the axis of revolution at every point in order to be a disk. So if I would have revolved this about the y-axis instead of y equals 3, I'd clearly have a disk. But I didn't do that. Okay, so now here's the hard part. You're figuring out your big R of y and little r of y. Big R of y, I think, is more straightforward just because you can pretty clearly see that no matter what, you're always going to be 3 units away from the edge. But if you would like, you can think about that as right minus left. So you're always 3 units away from the edge, or the right function is 3. Heading to the outermost point, the left function is 0. Okay, so right minus left. Or again, flip it around and look at it as top minus all the way to the bottom to get to the big R. All the way to the bottom. That is big R. Now it's going to be sideways R when I reflip it. Okay. Little r is going from the axis of revolution to the inner edge of the figure. That's little r. And for little r, again, we're thinking right minus left. The right function is 3. The left function, well, I need to rewrite this because right now I can't write it as 3 minus x squared. That wouldn't be r of y. But I can get x by itself by taking the square root of both sides, and I would get x equals the square root of y. And if you're wondering, well, why did she take the positive square root and not do plus or minus? Well, it's because I only have half of a parabola, the positive half. So I don't need to worry about the negative half that would be to the left of the y-axis. So for the inner radius, we have 3 minus, and then that inside function is the square root of y. Yikes. And that is how we would set this one up. I mean, we have a little bit of work to do on it still, but the hard part would be done. All right, so let's go ahead and look at, oh geez, what's happening with my lead? R of y squared is 9. And then little r of y squared, well, we're going to FOIL that out. This is 3 minus the square root of y times 3 minus the square root of y. And you're going to get 9 minus 6 root y plus y, because the square root of y times itself is just y. And since you're going to have to integrate this, you'll probably want to rewrite that with a rational exponent. Your integral then for volume is pi times the integral from, in our case, oh, you know what I did? I mean, it's not the end of the world. It's just a little tiny notation issue. I want this to match. We're technically going from C to D in this case. I know it's arbitrary, but I'm, pedantic about these things. So I'm looking at where do we go from y equals what to y equals what as I'm integrating. So I'm going from y equals 0 all the way up to y equals 4. That's the region that I'm covering. So those are going to be my limits of integration. Then I'm taking big R of y squared, which is 9, and subtracting off the entire quantity, little r of y squared. And then we'll simplify. So 9 minus 9 is 0. Then we'll have 6y to the half minus y dy. And then we'll integrate. So 1/2 plus 1 is 3/2. Divide by 3/2, and you multiply by 2/3. Increase the exponent by 1, divide by the new exponent. Okay, 6 times 2/3 is 4, so it's 12/3. Since you're going to have to evaluate this, technically you're putting it in your calculator, so it's not going to make a huge difference. But if you're doing this by hand, the 3/2 power, side note, is y to the first times y to the half, which is y times the square root of y. If you're doing this by hand, you'll probably find that it's much easier to evaluate if you write it in radical notation. And then minus 1/2 y squared, and we'll go from 0 to 4. And luckily you have some nice values here, so you don't have to worry about anything weird happening with your radicals. 4 times the square root of 4 minus 1/2 times 4 squared. If I evaluate this at 0, I'm going to get 0. 4 times 4 is 16, times 2 is 32. 4 squared is 16 minus, or times 1/2 is 8. And then you should end up getting 24 pi for your volume. Okay. So I have one more example that I had planned to go over. It's technically 4 parts, A through D, but I really just want to go through the setups, and then I'll give you the answers to the integrals. And if you need help with any of those, you can let me know. And none of them should be like really tricky or anything. They're going to be the kind of integrals we've seen. Mostly I just want to focus on the setups. So this will be example 7. Find the volume when y equals 2x squared well, I should say when the region bounded by y equals 2x squared, y equals 0, and x equals 2 is revolved about the following axes. The first one we're going to look at is the y-axis. So let's go ahead and graph this. We might want to just jot down a quick graph of this each time because we're going to mangle it each time. That's what we do around here. We mangle our graphs. Okay, so the y-axis is the vertical axis of revolution. So that means no matter what, we're looking for dy's. We're looking for big R of y at least. Maybe little r of y. We'll have to see if we have a disk or a washer. So let's go ahead and draw this out. 2x squared is your standard parabola, but it's being stretched vertically by a factor of 2. So if x is 0, y is 0, that hasn't changed. But now if x is 1, y is 2. And if x is 2, y is 8. I don't have a whole lot more space here. We're bounded by y equals 0, which is the x-axis, and x equals 2. So the binding here, sorry, let me fix this off to the side a little bit. X equals 2. And this point we said was at 2, 8. So it's still a little bit off. Oh, it's going to drive me crazy. Eyes on the prize. There it is. Okay. So it's really important that we pay attention to this. It's not saying x equals 0, which is the y-axis. If that was the case, we'd be looking at this piece between the y-axis and the graph. It's saying y equals 0, which is the x-axis, and x equals 2. So we're bound here. And we're revolving it about the y-axis. So you ask yourself, is this a disk or a washer? It is only touching the axis of revolution at one point and one point only. So this does not bode well for your hopes and dreams of having a disk to work with, because disks are easier. But that's okay. It's definitely a washer. It is not flush up against the axis of revolution. It barely even touches it except at that one point. So it is a washer. So let's go ahead and determine big R of y and little r of y. So big R of y, and if you would like, I would strongly recommend you draw your rectangle here, but we're always drawing our rectangle perpendicular to the axis of revolution. So it's going to look like that. And again, I think the outer radius we can clearly see no matter what is going to be 2 units. So I'm always going, and I'm going to write this, maybe it seems backwards to you, but it's always right minus left. This is your big R, 2 minus 0, right minus left. Or if you're just eyeballing it and you're like, yeah, clearly it's 2, that's fine. You don't have to show me the 2 minus 0 part. I get it. Little y, you're still going right minus left. For little y, remember that we're taking off this space that's in between the region and the axis of revolution. So when we go right minus left in this case, I'm starting at the figure and I'm moving my way left to the axis of revolution. Now, in order to write this, I'm going to have to fix my function, because right now it's written as y equals 2x squared, but I need it to be written in the form of x equals some expression in terms of y. So I can rewrite this as y over 2 equals x squared just by dividing both sides of this equation by 2. And then I can say that x equals the square root of y over 2. And again, it's not the plus or minus square root because I only have the positive piece of the square root function. Okay. So my inner radius is going to be x equals the square root of y over 2. So that's going to be just, I'm going to write it as the square root of y over 2. The whole thing goes in the radical. And then minus 0, because as I go right minus left, I'm just subtracting off x equals 0. So it's x equals the square root of y over 2 minus x equals 0. So this would be your outer and inner radii. These would be your outer and inner radii. And of course, you're going to square those. Oh, that's supposed to be a little y squared, or little r, not little y, sorry. The square root of y over 2 squared is just y over 2. So your setup here is going to be pi times the integral from, and remember I'm going from c to d here. I'm looking at a dy integral with r of y and r of y. So I'm not going from 0 to 2. I'm going to be going from 0 to 8. So I'm covering this whole region vertically. And then you'll have 4 minus y over 2 dy. And the answer that you should get is 16 pi. For some reason, I have something else here with a weird like notation on it. So now I kind of feel like maybe we should, it's very basic, straightforward integral. I'm sure it's fine. Famous last words. Okay. You can check that on your own. Let me know if you have questions about that. Like I said, I really just mostly want to focus on the setup here. For part B, we're going to rotate this about the x-axis. Now, if you don't want to redraw the figure for B, that's okay, because there's really not a whole ton to do for B. For part B, we're going to revolve this about the x-axis. That means you have a disk. In this case, your entire region is flush up against the axis of revolution. It touches everywhere. So you will not need to worry about having a situation where you have a washer. Your entire region is butting up to the axis of revolution. And the axis of revolution is horizontal. So that means that you're going to have an R of X situation. Oh, sorry. Okay, so you have a disk, and you're going to need the radius, R of X. I'm going to just jot this down real quick because I want to be able to look at it, but it doesn't have to be totally exact because we've already seen it. This is a point at 2, 8. If I need my R of X, remember we're drawing our rectangle perpendicular to the axis of revolution. That means it looks kind of like this. And we're looking for the height of that rectangle to find R of X. And the height of the rectangle is just the function definition. This is y equals 2x squared. So no matter what, it's always going to be this high. But you can also think of it as top minus bottom. The top would always be, all the time, lying on this curve, 2x squared. And the bottom is always going to be represented by y equals 0. So top minus bottom is 2x squared. And then whatever you do, don't forget to square it. So 2x squared, quantity squared. So you're taking 2x squared and multiplying it by itself. 2 squared is 4, x squared squared is x to the 4th. And then the last thing you need to do is just set up your integral. So we're taking pi times the integral from, and now I'm going from a to b. I'm using x limits for my dx integral, and I'm going from 0 to 2 of 4x to the 4th dx. Because I didn't have a washer, I don't need to worry about anything else inside this integrand. I just need to worry about including r of x quantity squared, big R of x. And when you integrate this, you should get 128/5 pi. All right, we'll look at two more things that we can do with this particular one. C, we're going to revolve this about the line y equals 8. So again, we've seen this picture a couple of times now. I'm going to jot it down real quick. We had this point at 2, 8. We had this parabola running through. We cut it off at 2. If we revolve this about the line y equals 8, well, that's the horizontal line that goes through y equals 8. Now you can see that if you were to revolve this about the line y equals 8, you would indeed have a washer because you have a whole segment here where the region isn't even touching. We already talked about revolving this about the x-axis, which was a disk. But about the line y equals 8, we definitely have a washer. But we do have a horizontal axis of revolution. That means we are looking for r of x, little r of x, and dx. So your big r of x is going to be the distance, big r of x, sorry, we're going about this one. I was thinking about this in terms of what we did on the last example, but we're moving our axis of revolution. Your radius for your big R is just going to be from the axis of revolution all the way down to the base of the figure. So no matter what, we're going to make this a little bit more, I don't know, that's supposed to be an R. No matter what, we're looking at top minus bottom, 8 minus 0. And I think this one too is easy to see because you can tell that it's 8 units from the bottom, the base of the figure to the axis of revolution. Little r of x, again, we're going top minus bottom. The axis of revolution to that inner edge of your figure. That would be little r. So I'm starting at 8 again. That's my top, but this time the bottom function is this parabola 2x squared. Oh gosh, I have to wrap this up. Well, here, I'll just give you r of x quantity squared. 64 minus 32x squared plus 4x to the 4th. And when you set this integral up, we're going to take pi times the integral from, well, x equals 0 to x equals 2. So we're looking at the x-axis here to get our limits of integration. So we're going from 0 to 2, and you're going to take 8 squared. So r of x squared is 64 minus 64 minus 32x squared plus 4x to the 4th dx. And you should end up with 896/15 pi. Okay. The last thing I wanted to look at here was the line x equals 2. So again, I mean, I'm just redrawing this figure over and over again at this point. The line x equals 2, if I'm revolving about this line, is a vertical axis of revolution. So that means that I would be looking for r of y and dy. And I kind of gave that away there because I'm not looking for a little r of y. Reason being, this would be a disk. If I were to revolve this region about x equals 2, well, my region is flush up against the axis of revolution at every single point in the region. That's why it's a disk. Your radius, big R of y, is always going to be, if you're going about the line x equals 2, vertical axis of revolution, you're going to be looking at right minus left. So you're going from the axis of revolution to the outer edge of the figure. So in this case, we're looking at 2 minus, and then this function. This function was y equals 2x squared, and we solved for x, and we said it was the square root of y over 2. So when you set up your r of y, you're looking at 2 minus the square root of y over 2. Okay. So right minus left. So you're going from your axis of revolution, in this case, over to your left edge of the figure. Now, if you're confused about that, thinking like, why did I do that? Well, I mean, think about the fact that you're not rotating this about the y-axis. You're rotating it about this line x equals 2. So you're not, it has nothing to do with what's going on here. So you wouldn't just use this function value. If you did, you'd be missing everything that's happening between here, and you'd be getting the wrong volume. Okay, so that's r of y, and I will give you the answer here. Oh, I might as well tell you that your integral is going from, if it's a dy integral, it's going from 0 to 8. R of y squared dy, you should end up getting 16/3 pi. You check that on your own time if you'd like. Like I said, mostly I just wanted to go through the setup with you so that you had a good idea of what changing the axis of revolution is going to do by looking at this same figure from a bunch of different angles. So I really love this example. I think it's awesome. Okay, that was anything I had to tell you about 6.2. It's discs and washers. We're going to talk then Wednesday in class about shells. We're going to kind of switch everything up. Some students like shells better. Some like discs and washers better. You might find that depending on the type of example you're looking at, one is much easier than the other, and that's true. A lot of times if students see a washer, they're like, ooh, I'd rather use a shell with this, because with a shell, it doesn't matter if you have a disc or a washer, you do the same thing. I don't know. I think because students learn discs and washers first, they tend to always want to do discs and washers all the time. I've found over the years that shells can be easier, but I don't know. Keep an open mind. It kind of depends on your problem. If it's just a straightforward disc, discs are usually no big deal. If you have questions, please email me and let me know. You'll have a quiz Wednesday. I already mentioned that. And Wednesday will over 6.3. I mentioned that. And then the next asynchronous video that I'll make for you will be about 6.4, which is about finding volumes using cross sections. We'll focus a little bit on that, and then we'll get into work in 6.5. So really focus on this volume stuff. It's going to go on for a while. It can be challenging. You just have to do a bunch of problems. I don't know how else to say it. You've got to just try a bunch of different ones and try to find their radii and see how far you get. But please do come to student hours on Monday at 5 o'clock. It's from 5 to 6. Show up, ask questions if you have them, hang out and do homework if you don't have them. And when you have a question that pops up, you can let me know. But I'll be there, and I would love to go over some volume questions with you if you have them. I'm going to put some homework up for you on Achieve. I'm going to do that tomorrow. For you, that'll be, well, I don't know, by the time I post this video, who knows? But I'll have the homework up by Friday for you. I know you're still going to be doing area anyway, so it's going to take you a while to get to the volume. All right, you guys, have a wonderful rest of your week. Enjoy your weekend, and reach out if you have questions. Check out the tutoring center also. It's a very helpful resource. Okay. Adios.